Hi guys, in this video I'm going to be going through what I learned about derivatives. Um, so in this video I'm just going to be going through the basics or the introduction to derivatives. I'm not actually going to be going through the formula here. I'm just going to go through all the prerequisites and what you actually need to know as background knowledge to understand derivatives. The reason I'm making this video is just for myself, really. In the future when I forget about derivatives, which is undoubtedly going to happen, I'm going to want to watch this video and just refresh myself on the concepts. So yeah, let's get right into it. And obviously this is for other people as well. If anyone's watching this, I hope this video and the part 2 video, which I'm going to make, I hope it's useful to you. So let's get right into it. So I've separated this by topic, so it's a little easier to go through. And it's a little bit easier for my future self to go through this as well. So let's start with the slope. So slope or rise over run is the average rate of change between 2 points. This could be 2 points in time or 2 points on a graph, which is what I have here. So I have a graph f of x, and it's a straight line. It's some straight line. It doesn't really matter what straight line it is. It's some function which is a straight line. And I've marked 2 points on this graph. The x value is x1 and the y value is y1 for the first point. And for the second point, the x value is x2 and the corresponding y value is y2. So this is the basic formula for slope. This is a pretty fundamental formula. You learn it in your algebra class. But slope is equal to change in y over change in x, which is delta y over delta x, which is y1 minus y2 over x1 minus x2. So it's basically, it's all slope is saying, it's this distance here divided by this distance. So it actually represents the average rate of change between these 2 points. So over here, I've just written it in a different way using some different notation, but it's the same thing, same concept. Let me just plug in my device so that the recording doesn't stop. All right, there we go. All right, yeah, so I've written this graph in another way and the slope in another way as well. So we have the same graph, f of x, and the x-axis is x, and it's the same line, but the first point I'm putting as the x value is x, and the y value is f of x. And for the second point, the x value is x plus h. So we took this first point and we increased the x by some arbitrary number h. And the corresponding y value would be f of x plus h. Now it's pretty obvious to see that the difference or the distance between x and x plus h is h. We just need to do x plus h minus x, which is h. And this y distance would simply be the difference between the two corresponding y values, which would be f of x plus h minus f of x. So to calculate the slope, we would say slope is equal to change in y over change in x, delta y over delta x, and we would say that it's equal to f of x plus h minus f of x. Remember, that is just that distance right there, over h. H is the distance between the two x points. So this is the slope of a straight line, and it's key to note that this is the slope of a straight line. So if I take two other points on this line, let's say I take this point and this point, and I calculate the rise over run for those 2 points, it would be the same result as we got the slope for these 2 points, because it's a straight line. The rate of change doesn't change. It's the same. You get the same increase in y for x, and the ratio is the same. All right, so now that we know about slopes, let's see how we can integrate slopes into curves. Now, how can we think about slopes when it comes to curve functions? Well, we can choose 2 points on the curve, join them with a line, and find the slope of that line. This line is known as a secant. So I have the graph or the function f of x equals x squared here, and I've labeled it up to x equals 2. And I have 2 points, 1, 1 and 2, 4. So those are the 2 points I've labeled. And I've drawn a secant line through these 2 points. Now, a secant is a line that intersects a graph at 2 and only 2 points. And that's that secant right here. It only intersects the line at 1, 1, or sorry, it only intersects the graph at 1, 1 and 2, 4. So I'm going to calculate the slope of this secant line. So the slope is equal to change in y over change in x, equal to delta y over delta x, which is equal to 3 over 1. And I got that 3 from here. That's that delta y, which is 4 minus 1. That's 3. And then I got this 1 from 2 minus 1, which is the difference between the two x values. And I got a slope of 3. Now, what does the slope of 3 actually mean? Well, let's check it out. So above is the function f of x equals x squared, or at least part of it. I've connected the points 1, 1 and 2, 4. The secant joining these 2 points has slope 3. Well, what does this mean? This means that on average, for every unit increase of x, y increased by 3 over the interval 1, 2. So for this graph, and for this interval from 1 to 2, on average, every time I increased x by 1, y increased by 3. That's pretty obvious here. That's literally the example we have here. So we increase x by 1 and y increase by 3. But the key thing to note here is that this only works over the interval 1, 2. The slope is only 3 for this interval. If I chose the interval 1 to 3, so let's say I'd marked 3 somewhere here, and I had the graph up here, and I had marked that point, or it would be something like here, right? Let's say I'd marked that point, and I drew a secant through those 2 points. The slope of that secant would be different from the slope of this secant from 1 to 2. That's because this function is curved. The rate of change is actually not constant. It's not increasing by a constant value, to say. In fact, it's actually accelerating. You can think of it as that the rate of change is accelerating. So for here, every one unit increase of x, we would increase x by 1. We would increase y by 1. But for here, every unit increase of x, we increase y by 3. And for the next one, every unit increase of x, we would increase y by 5. So the rate of change, or the slope, is not constant along this curved function. And that's true for all curved functions. Here's another example I have. So here is the graph f of x is equal to 1 over x, also called a hyperbola. And I have the graph here. That's the curved line right there, the curved arc. And I've marked 2 points, half, 2, and 3, 1/3. And I've drawn a secant line through those 2 points. And here I'm calculating the slope of that secant line. So slope is, again, change in y over change in x, delta y over delta x. So I've chosen to use this point first in calculating the slope, and then this point. We could have done it vice versa as well. We would get the same result. So I'm doing f of 1, f of half, minus f of 3, which is that distance there, over half minus 3, which is that distance there. So the change in y over the change in x. Simple stuff. So that evaluates to minus 2/3 in the end. And we get a negative slope, and that makes sense because the slope of this line is negative. From left to right, we're actually decreasing in y. Our y is going down. So for every increase in x, we're actually decreasing y, which is why we have a negative slope. So above is part of the function f of x equals 1 over x. I have connected the points half and 2 and 3, 1/3. The secant joining these points has slope minus 2/3. This means that on average, between the interval half to 3, for every unit increase of x, y decrease by 2/3. Slope is the average rate of change. So over this interval, on average, for every unit increase in x, y decreased by 2/3. That's what the slope means. It's the average rate of change over an interval. All right, so that's secants, using secants to evaluate the slope of a curved function. But it's not really the slope of a curved function, is it? Because the slope of a curved function actually changes. So we're only evaluating at a specific interval. But what if I wanted to know the instantaneous rate of change? Now, if you actually say this out loud, it doesn't really make sense. So let's actually go deeper into it. What if I wanted to find the rate of change at a particular point? This is paradoxical because you cannot measure change at a point. Change implies an increase or a decrease. So I have this function here, a curved function, and I have this point here. What if I want to measure the rate of change at that point? Now, that actually doesn't make sense because think of it like this. Let's say this curve function was modeling the the distance traveled by a car. So we can see here that the velocity is actually increasing. So at this point, the car is traveling quite slow. For every unit increase in time, the distance isn't increasing that much. But here we can see that for every unit increase in time, distance is increasing quite a bit. So the car is faster here, or the velocity is faster. So, but to calculate velocity, you actually need 2 points in time, don't you? You need to know the distance traveled here and the distance traveled here, and how long each one took, and then you can calculate the velocity. But what if we wanted to know the velocity at this point? What is the rate of change at this point? This is kind of like me asking. This is kind of like me telling you, okay, look at this car. It's moving, yeah. But I'm gonna take a picture of it now. Tell me the speed of the car in this picture. You wouldn't be able to tell me, right? It's absurd. You can't tell me because you can't evaluate the distance traveled over a specific time. You're only looking at a snapshot in time, which is basically what I have here. This point here is a snapshot in time, and I'm asking what is the rate of change at this point? It doesn't make sense. But let's actually just march into the unknown and let's see what we can discover from this. Well, we know that the slope measures the average rate of change between 2 points. So if I had these 2 points, here, and I drew the slope, I drew the secant line, and I calculated the slope, then I could measure the average velocity over that interval. But it wouldn't give me the velocity at that specific interval. But what if we brought these 2 points, closer and closer and closer? So I have these 2 points here. What if I brought them ever so closely? So I took these 2 points and I brought them ever so closely. Would I be able to get a good approximation for the rate of change at that point? Maybe. Let's check it out. So I have a bunch of graphs here, and this is leading on. Remember, we're asking ourselves, what if we brought these 2 points closer and closer? So I have the graph, a curved graph here. It doesn't matter what graph it is, but it is some curved function f of x. And I'm starting here at this graph here. So I have the curve function. I've drawn 2 points. The x value of the first point is a, and the x value of the second point is a plus 6. So it's just this plus 6. And I haven't marked the corresponding y values, but it's not that important. What's important is that we note that I've drawn a secant to this line, and we note the slope of this line. Now, what I'm going to do in the next graph, I'm going to keep the point A fixed. So this point I'm keeping fixed, but I'm going to take the second point that we have, and I'm going to reduce the x value by 1. So previously we had a plus 6, and now we have a plus 5. So you can see that this point has reduced in its x width, but it's also reduced in its y. It's come down a little. So we can see that the slope is slightly less steeper than this one. It might not be too obvious, but let's keep going. So here I have a and a plus 4. Down here I have a and a plus 3, a and a plus 2, and a and a plus 1. So these 2 points are only one distance away from each other on the x-axis. Let's compare that. So we have a plus 6. The secant line is pretty steep. But on this final one, it's a little less steeper, and it's considerably less steeper. It's almost like a steepness of 1, and this is a steepness of 2. So we can see that as the distance between the 2 points decreases, the secant line actually becomes more and more like something. It's approaching something. But what is it actually approaching? Well, as the distance between the 2 points gets smaller and smaller, the slope of the secant becomes less steeper. In fact, the secant is looking more and more like the tangent to the graph at x equals a. Now, what's a tangent? A tangent is a line that only intersects a graph at one point. So the tangent at a for this graph would be a line, an imaginary line. Let's say we had a line here, and it would only intersect the graph at that point a. And we can see we have the secant here. As we bring the 2 points closer and closer, we're approaching that tangent. The secant line is approaching that tangent. So let's actually investigate the slope of a tangent. I hope this is clear. I hope it unblurs. Let's see. All right. So the slope of a tangent. If the slope of the secant between 2 points measures the average rate of change over that interval, Perhaps the slope of the tangent at a particular point measures the instantaneous rate of change at that point. So I have the graph here, that problem we were trying to solve, the instantaneous rate of change for that point. And I'm drawing the tangent line to the graph at that point. I've written here that logically, the slope of the tangent would be the instantaneous rate of change at that point. I think the camera is a little blurry. I wonder, let me just shake it a little. Clear things. Come on, refocus. Okay, I think that's a little bit better. Okay. But how, so I've written the tangent, I've drawn the tangent at the graph at that point. Now I want to find the slope of this tangent. But how can we find the slope of a tangent line when we only know one point? The definition of slope, rise over run, requires 2 points to be calculated. Slope is equal to y1 minus y2 over x1 minus x2 equal to delta y delta x. This calculation requires 2 points with 2 x values and 2 y values. But I only have a single point here, and that's all I know about this tangent line. It intersects the graph at that single point. How can I calculate the slope of that tangent line? I need more information. Well, this is where the idea of transforming from secants to tangents actually comes in. But let's continue. So on the next page, from secants to tangents, let's read. We saw previously that by reducing the distance between 2 points, the slope of the secant joining them approaches the slope of the tangent at the first point. So that's what we saw before. The slope of the secant joining the 2 points gets better and better, and it gets closer and closer to the slope of the tangent as the distance between the 2 points decreases. So that's basically what that paragraph there, right there is saying. All right, and I have another quick reminder of that. So I have a graph f of x, a function f of x. I've graphed it, and I have one point at x equals a, and another point at x equals a plus h, some arbitrary h value. And I've drawn the secant joining those two points, and we notice that when we reduce h, so we bring the points closer and closer together, the slope of the secant actually becomes much less steeper. And we can see the slope of the secant actually approaches the slope of the tangent at A. So if I drew the tangent at A, it would look a little something like this. It will look a little something like this. And we can see that the slope of the secant is approaching the slope of the tangent. I've written here, as h approaches 0, the slope of the secant joining the 2 points approaches the slope of the tangent at x equals a. So here's the interesting bit. What if we took the limit as h approaches 0 of the slope of the secant line between points a, f of a? Remember, a, f of a is that point right there. A, and the corresponding y value is f of a. So I have that point, and the point a plus h, comma, f of a plus h. That's that point right there. A plus h is the x, and the y value is f of a plus h. So what if I took those 2 points, drew a secant line, calculated the slope of that secant line, and I took the limit as h approaches 0. So that's basically saying, what if I go to the end? Let me ask myself, what does this slope approach as h approaches 0? So as h approaches 0 means as a plus h approaches a. So as these points become closer and closer together, what does the slope approach? Now, if we were able to calculate that, we would have a really good constant approximation for the slope of the tangent at x equals a. If we were able to ask ourselves, well, what happens as h becomes smaller and smaller until it eventually goes to 0? What happens to the slope? It would match, or it would be a pretty good approximation for the slope of the tangent at x equals a. And this core idea is actually the main idea behind the derivative. And I think the next page actually goes, the next page actually goes over the derivative. So that's what we'll do in the next video. We'll actually see what the derivative is. We'll see the formal definition, and we'll see some concrete examples. So this is the main idea of the derivative. We're taking the limit, or we're actually asking ourselves, what happens to the slope of the secant as h becomes smaller and smaller and smaller, or as it approaches 0? Well, the slope will approach the slope of the tangent, and that's exactly what we want. So that's what we'll see in the next video. Thank you guys for watching, and I hope this helped to anyone who's watching and also my future self who's watching. So thank you, and I'll see you in the next one.